As Pete was saying, I have too many years working with data in a broad range of data. I started actually working with industrial manufacturing data, steel production, and then transportation data, city data, telco data, and quite a bit with financial data. And it was, from each one of the changes, it was fascinating diving into the data and getting your hands dirty, which I guess is what the community here likes to hear about the data. But I want to start explaining some of the shortcomings of all the data that I worked with. And basically, though this data can solve a number of very relevant challenges on each one of these respective industries, they fall pretty short in solving some of the major challenges that humanity has today. So if you look at humanity as a whole, people globally, and I'm going to go through some very, very basic examples. You know, if you look at food, this is the number of land that is being used year over year for food production in order to feed humankind. As you know, we're being very successful in food production, not so much in food distribution, but we are producing more food than humanity needs, but this is at a high cost in terms of environment. So if we want to continue increasing food production, by 2050, there'll be about between 9,000, 10,000 of us here. We'll need to double food production from today to that year because we need to feed the people, but we also need to feed the animals. So if we want to do that in a sustainable way, we basically have three options. Either we go and plant in the Sahara, or we deforest the Amazon basin, or we find new alternative seeds and ways of more advanced ways genetically of producing foods, or we do what we're doing more efficiently. We use the land we are already using more efficiently. And there's a lot of evidence to show that this last option is preferred over the first options, and data is very relevant in order to achieve it. Let's look at another challenge here. This is global primary energy consumption. So as you can see, not only is it's growing exponentially like most of the indicators that we're showing, but it is also growing along some of the lines we're not so interested in growing, like coal and crude oil and natural gas, because those are finite resources. So we need ways of managing much better, not only how that grows in order to use energy more efficiently, but also in the distribution between different energy sources. So this is a huge challenge that we have ahead, not only at the level of the production, but also at the level of the global distribution of the energy. Another huge challenge that we're struggling with is the management of natural resources. So what you see there, that graph shows a mixture of forest gain, forest loss. What you have, loss of forest, is in red, very worrying, along the equator, which is where most of the canopy is concentrated. But you can see on the other side that you have net gain of forest in many of the developing countries. So there's there's some positive indicators that if we manage to arrange the production and the use of land more efficiently, related with energy, related with food, we can regain forest production. And we need to manage this. The thing is, how do we manage this, and what kind of data? What is the solution for this? So we know a couple of things, that whatever solution to these huge problems there are, it has to be global. We cannot have a solution that's good in Spain, but then it doesn't work. We're going to have food solution that is good in Spain that doesn't work for the rest of Europe. We can't have regulations that finish in any border, because we know that in the globalized world anybody will be able to bypass the regulation by just jumping across the border, we need to have that solution to be global. So we need to look at it globally. In a way, what we need, and we don't know which is the right solution for each one of those, but at the very least, what we want to know is whether one solution is better than the other one. As we don't doubt that creativity, human creativity, will come up with many possible solutions for all these challenges. I don't doubt about that. But what I'm not sure is, how are we going to describe which ones are good and which ones are not so good? So in a way, in Satellogic, what we said is, we need something like a Fitbit for the planet. That at the very least, we're measuring each one of these solutions, each one of these policies as they are taking, each one of the changes, and we're able to tell this is good, this is bad. And in order to do that, we need to do it at a planetary scale. And there's many ways of doing this. We could send aerostatic globes, we could cover the planet with drones, we could have Earth sensors every 10 meters to measure all this, we could empower our telephones to do more things that they're doing, but that's not at a planetary scale. Even if we have our cell phones, the land cover of the Earth by humans is very limited. And a lot of these things, food production, energy production, are happening where we are not, right? In remote places. So the reason Satellogic was never intended to be a satellite person, it was a company, it was intended to be a solutions company for these kind of challenges. Turns out that satellites are just great as remote sensors for acting as a Fitbit of the planet. The challenge then was that building a satellite that took 1 meter resolution imagery of the planet 10 years ago cost $650 million. Okay? So the cost of opportunity of having each one of those images and the coverage of those images was just too limited. In order to have daily, let's say, coverage of the planet at 1 meter resolution, you need hundreds of those satellites, so it simply does not scale. So we needed to make satellites much cheaper, much lighter, much smaller, okay, because cost also is related with the launching cost, and weight has a lot to do with that. And if we managed to do that, we could scale that coverage. We could have images of the planet every single day, every single week. And most importantly, if I managed to do a satellite for this in 1 million, and I'm talking 1,000 times improvement from the previous version, I reduce my learning cycle. And as you know, with technology, the key is reducing your learning cycle. If you manage to do anything, any kind of experimental environment, anything which allows you to learn faster, then you enter into a cycle that you really can do breakthrough stuff, right? And you need to do all that reduction while preserving data quality. And what I mean by data quality here is taking good 1 meter resolution images, because why 1 meter, why not 10 meters, for instance? Right now you have free imagery of the world every 5 days, thanks to the Copernicus, to Sentinel satellites, to the Copernicus constellation, or to Landsat data, a little bit lower resolution, but it has 10 meters, 15 meters. And the reason for 1 meter is 1 meter is the scale of human beings. It's our scale. We live at 1 meter scale. You know, our roads are this size because we are this size, and our cars are this size because we are this size, and our machinery and buildings and everything we do, our impact in the planet is in the meter scale. If we were 1 centimeter in size, probably we would need much higher resolution satellites than we do now. So we did that. And we currently have 8 satellites in space. And these are this is a sample image of Barcelona at 1 meter resolution, taken by our satellites earlier this year. And you can do Barcelona, which is heavily populated, but on the other side, it's also heavily populated with sensors. So the value of doing Barcelona or any other large city is not so important. And I'm sure that many of the data that most of you guys work here, be it transportation, Uber, Lyft, a Cabify, a Glovo, a financial data, can give a very good image of what's going on in Barcelona, but not so good in West Liberty, Iowa, right? Where a lot of the production of, in this case, corn and soy is taking place. Most of the production in the United States, that's called the Corn Belt in the United States. And on top of that, what we did is not only added a 1 meter resolution camera, we did what's called a hyperspectral 30 meter resolution camera. So hyperspectral, and I'm mentioning this because I'm going to show you examples on computer vision on each one of those sensors, so you need to understand what they do. A hyperspectral means that basically our hyperspectral camera looks over the visible scale plus the near infrared, but instead of having 3 different channels like we would have, it has 30 different channels that looks into very narrow bands. In a way, it's like looking at colors with superpowers. Like where we see maybe the same plant having a green leaf, a hyperspectral camera would look that could be a million shades of green, and thanks to those shades, you would know the health of the plant. So you can do a ton of nice things. This is Gambia here. For instance, here in Gambia, we're looking at the presence of algae in the rivers. And the reason we're looking at the presence of algae is because where those algae live some tiny snails. And those snails are where these parasites that are giving Gambians huge headaches because they're causing gastro problems in children inhabit in these are parasites that inhabit in these snails. So they're transported by these snails. So by looking at the algae, you can anticipate where this disease, this parasite disease, will be spreading, because where you have huge growths of algae, you will have a higher probability of that disease spreading in nearby towns. So you already can see through a very simple example how this new source of data can help address some challenging problems. And here, just a curious example is we not only do images, we also do video. This is a not so good video, but what you're seeing there all the time is Venice. And what I like, that's Venice, you know, the islands around Venice and so forth. And it was the first video we got, so we're proud of it, not because of its quality, but because of its originality. And what's really interesting about this video, it gives you an idea of how fast these satellites move in order to capture the data. The video, as you've seen it, started shooting when the satellite was over Moscow, and it finished shooting when the satellite was over Cairo. So when you have these two sources of data, the multispectral data and the hyperspectral data, you can address, as I said, challenges along many different sectors, government sectors, agriculture, infrastructure, in many different ways. And what I'm going to show you one is very concrete examples of the basis of those challenges, because you need to build a solution, for instance, for people who manage remote, very expensive oil infrastructure. It's really expensive to send people there, airplanes, drones, so doing it remotely will save them a lot of money. But in doing that solution, you need to talk their language. You need to do something that will integrate with their oil field management systems and so on. But what underlies always these systems, right between the data and their solutions, is computer vision. You know, machine learning, computer vision, image processing. So these are the four, and you will see nothing new here, not meaning that everything is solved here. This is the four main, let's say, algorithm types or algorithm groups within computer vision that are relevant in remote sensing: segmentation, detection, change detection, meaning detection plus looking things over time, and regression. Okay, and this is what you're seeing there is an actual image of one of the projects we have. This is a large forestation, right, in a forest operation, and you're using segmentation to determine where's the actual forest, where's the actual trees, and you can see those blue lines there, versus where there's nothing. You're using detection to actually detect the individual trees and count them. We're using change detection to look at the evolution of plague, of harvesting, of the different activities that take place within afforestation. And we're using regression to estimate from the time series of those trees growing the potential value of all deforestation. Single problem, we're using all those algorithms there. Let's see some more detailed problems. So segmentation, this is the classical one. This is the one that probably, it's been around for a while since Landsat started sharing their images, remote sensing community, and some computer scientists started looking at how to do land use. Basically, it was done on image processing, huge jump when machine learning came up, and in the last couple of years, as we're having more data available for companies like us, but a lot of other companies that are following the same goal, there's a boom of this. Last CVPR, there was a huge challenge on, for instance, on land use, which has been a traditional problem for a while. So you can see here, this is Sabadell actually. This is here, I tried to take pictures near Barcelona. So, and this is the typical problem of land use, which is assigning a pixel to a type of use or to a type of cover that land is having, be it different types of forest, agriculture, residential buildings, industrial buildings, and so forth. Only doing that, you can do a lot of interesting stuff. Segmentation, another one here. So this is another problem. This is in this case, this is called rapeseed, which is the crop that is used for canola oil, which is it's growing a lot. It's quite good because it's replacing palm oil, which is not so good, right? And so it's growing in South America, it's growing in China, it's growing mainly in Canada. It's beautiful because it has all these yellow flowers. So it's important because since it's growing so much, the growth of this by the individual farmers is not precisely monitored in many ways. And that needs to be monitored to understand what the impact of that growth will have on the market. So we're detecting automatically canola oil from plantations, and this is a very simple, well, it's simple. It's not so simple, but it's a solvable segmentation problems. And you can do more stuff. Here what we're doing is training a neural network, what we would call semantic segmentation. Instead of doing it by a simple 0-1 training, here we're training a neural network, for instance, on roads or on rivers. So you have this image here, and we want to isolate buildings and different types of crops, and as I said, land use, roads and rivers. And that's what you're seeing there directly is the response of the trained network on roads here and on rivers over there. And you can do more traditional detection. In this case, we're detecting boats in a lake. So this is a recreational area, national parks that want to assess the human use of that national park so they can control when things are going out of hand. When there's too many people, they can restrict the entrance and they can restrict the usage of the lakes in those national and recreational parks. This looks like, all of these look straightforward, tons of challenges within each one of these, tons of challenges to be done. So just to give you an example here, we're talking about a 15% error rate that could be easily taken to 10, 5, given more data. But really, if you want applications on this, you need to do even better than that. I was mentioning energy, production of energy. Here what you have is an oil field, and oil fields need to be looked from many different directions. Typically, the oil field belongs to the government, and it is given to different companies for exploitation. So the government wants to know that that is done in the right way, for instance, from an environmental purpose. And each one of those companies want to understand each one's operations, and they also want to understand the other guy's operations, right? So there's a lot of information that you can extract, and this is actually, the response of things like I showed you, that road-trained neural network in a pad detector and an oil pipe detection on this particular image that you see here. That's the response there, and that's the actual ground truth that we're obtaining, as you can imagine. And I'm going to finish with some of the challenges, top challenges we have. But as you can imagine, the difficult chromo, like we say here, there is the ground truth. The difficult thing to obtain is the ground truth. So now if you add to detection, you add time, you have this kind of situation. This is exactly the same region, right? And you can say, okay, do a change detection algorithm. If anybody, for those here who are aware of image processing and computer vision, what you have there in the middle, that's an oil spill. And that's exactly what you want to detect. That's what your system you want to detect. One day there's an oil spill, you're looking at the planet, and you know there's an oil spill there, and you act upon it immediately. The problem is that any traditional change detection of two images will say that those images are essentially different on every single pixel, if you look at that. So our challenge was to train detectors in order to look at these. These are exactly, once again, these two images that you're seeing horizontally are exactly the same images. And the regions that you see surrounded by red is where we've seen changes, relevant changes. So you would say that semantic change detection, in the sense, I don't want to look for vegetation changes, I don't want to look for seasonal changes because there's a drought or because it rained right before an image or any other type. I just want to look where there's new, in this case, oil pads, oil pools, roads, in the other case, where there's a new oil spill. Or in this case, I want to look where there has been harvesting in forestry, and where there has been deforestation in large forests. This one is a nice one because here what you're doing is you're training a classifier on solar panels, and this is related to understanding energy, right? At a global scale. You're training on a solar panel, and you're actually looking at the image and the response, let's say, to a city or a certain region, to the solar panel detector at two different times, and by subtracting those, you can have those heat maps right away telling you where there were solar panels installed in that lapse of time. And you can do it, there's many more examples, but I kind of feel attached to these examples because every time I look at the images, those are exactly the same image, the same place. And you see that the most relevant changes are around. Even shadows are a problem here because the satellites not always take the image or capture the image from the same angle. It's a very tough problem. What you actually want to say is show me only the changes in the building, or show me only where the growth of the river might pose a problem to a certain type of infrastructure. And that's exactly what these detectors are finding. And finally, regression. I said segmentation, detection, change detection, and regression. You see here, in this particular case, we are fusing very different data sources to estimate soil moisture in rice plantations. So soil moisture is not so easy to detect because the plant covers the soil in many cases, so you have to look through the plants. So what we're doing is not only using the visible channels, but also using near-infrared, thermal infrared channels to build these, to regress the amount of soil moisture. And if you have this is the same, this is the soil moisture estimation, the water level indexes in the whole plantation. And if you have, in this case, what you have is for a certain rice field, the yield that rice field had at the end of a campaign. So a rice planting campaign can last about 4 months. Okay, so here you have regression plus time, where you end up having some kind of predictive analytics. So what I want to be able to do is at any time of the campaign, be able to predict the actual yield that I will have. Because in agriculture, a lot of people move by proxies. They're just saying, okay, I'm looking at the amount of hydrogen or the amount of water or fertilizers that I need at the end of the day because I want more yield. So if we're able to look at the actual yield, because we're starting to capture that information in week after week, predicting yield based on current situations, every week we can act on our plantation, not based on the water level, that is important, but not the only thing, but based on the actual yield. Same thing in this case, we applied the same for estimating future forest density. So with that, I showed you, I hope, some good examples of computer vision applied to these types of images across many fields. And I mentioned that in this case, this is a solution that is being developed of transforming these computer vision results into an alert engine for operators of oil pipelines. And you can have this kind of things across infrastructure, as I said, because you can manage roads and bridges and power plants and so forth, energy, food security, and also natural resources, governments, into cartography, policy and government. You wouldn't imagine, because we're used to Google Maps and we're used to OpenStreetMaps, and those are great where there's people. But there's not people, you know, most of the earth, there's no people, and they're really bad. You would imagine how bad the cartographic status of certain regions of the planet is today. And in order to start understanding, once again, what we need to do with the planet, you need to get that right from the beginning. So I wanted to finish by, especially because this is a technical community, to appealing to the technical skills and basically sharing with you that we're far from having this problem solved. So I chose a single problem, a single sector, let's say, which is the AgTech, you know, technology applied to agriculture sector. And the kind of holy grail in agriculture is what you see there, that tractor who's being told directly from the satellite the percentages of whatever, seeds or fertilizer or whatever needs to be applied in order to rationalize the use of resources, in order to optimize the productivity. Okay, and that would allow what I said at the very beginning, to have a much better use of current resources without depleting, you know, the jungle or the deserts, right? But even doing things here is very tough. And let me share you. First of all, there's a lot of variability between crops. You work for 3 months in order to do this great thing about soy and soy moisture or rice moisture that I showed. It won't work with wheat, right? It won't. It has absolutely nothing to do. But then you have, it won't even work with the same crop in a different region. So you have rice in Argentina and you have rice in China, whole different story, different soil, so you have to do it all over again. Think from it as a machine learning expert. The ground truth that you need that ground truth all over again in many places. And then it doesn't work on the same crop, on the same land, because you have genetic variety. And I might have this field here that comes out of certain variety of rice, and the field next door is a different variety of rice. So if I train a model on this field here, it just won't work on the field next to it. Same soil, same crop. Then, of course, it won't work between different campaigns, because I have same soil, same crop, same field. Next campaign, next year, first day, rains a lot. Everything's different from the rest of it. Whatever I inferred on the previous campaign won't work on this one. And on top of that, you have regulations. So across countries, you might have that certain types of fertilizers, that certain types of seeds are allowed and not. So the kind of measures that you can prescribe in one place or the other will be completely different. And that's only the variability issue in terms of learning. There's also the availability. And the typical lack of availability that we will find in many fields is the lack of ground truth, the lack of digitized data. And the truth is that in many sectors, you know, the farmers are still writing down in notebooks their observations, everything they write down, but in notebooks. So there's low levels of digitization. And availability in this particular field is also low because each learning cycle takes a year. It's not like the Drosophila, right? Like that you can do your genetic advancements really fast because of the generations. This takes a year. You know, so you need to test whatever you learn next year. And on top of that, this is one, you know, this is the kind of thing where startups are crashing like bugs against a light. You know, you can see active startups starting and ending their lives every single day because they don't realize these kind of things. For instance, the genetic lifespan of a certain crop variety, the average is 3 years today. So if I'm planting wheat, the probability in 5 years that the seeds, the genetic variety of the wheat I planted today is similar is very, very low. Okay? So that means that, imagine, first, from a machine learning perspective, first campaign, you have no idea. It's a new genetic variety, so you try to gather all the data you have. Second one, you have one data point, and the third one, you have 2 data points. Hopefully, you're able to predict something, and the next one, there's a different genetic variety, so there goes all your work. And on top of that, you have new sensors. I mentioned that hyperspectral sensor. It's very exciting to say, okay, we have hyperspectral data, but we don't have hyperspectral ground truth. So how do we infer from the ground truth we have that is measured, that is captured with other sensors there? And of course, all the things we're doing are very nice, and on top of all those things, we need to provide information to the farmers in real time. So there's many, but these are the 3 most relevant lines of research that are pretty hot today and are very relevant for what I do. Number 1 is automated data generation. Okay, I don't need to wait for the farmer for the whole year. I need to be able to simulate all these cycles. I need to be able to simulate the behavior of the genetic varieties. I need to be able to simulate and get data, even if it's not exactly the data that I need, in order to train the models that I need. One-shot learning, very important because of all the examples that I gave you. This is kind of self-explanatory. And one that I believe is huge is, of course, transfer learning and domain adaptation. For instance, if you look at regions like Europe, like in Spain, we're very advanced in terms of olive trees, right? And we have pretty much a good idea, especially in where there's expensive production, high value production. Probably you have a name and last name for every single olive tree there, right? And we have a lot of data points for the olive trees, and there's a lot of investment in gathering data. But then you go to the olive tree production in Morocco, and you have no idea. Okay, so maybe this kind of satellite data that you can have cheap or almost free in both Spain and Morocco can be a great transfer medium for all the things that you are able to learn with algorithms in Spain and apply in Morocco. So domain adaptation for places, moving from places where you have a lot of ground truth data available to places where you don't have ground truth available, especially because this typically agrees with places that you have high levels of development to places where you have low levels of development, will be huge. And that is a very classical machine learning and computer vision problem. So with these challenges, I wanted to finish and invite you to ask questions, and if, don't worry, we'll take a couple and we'll go afterwards outside for if there's anybody who wants to chat a little bit more about these challenges. Thank you very much.
Thank you very much, very interesting. Could you speak about data volumes and data stack to be able to achieve that? Something that you're dealing with?
I didn't get the last part. You mentioned about data stack?
Data stack, like are you using a Hadoop cluster to process the data, or are you using other technologies?
Yes.
And data volumes, are you dealing with very big data sets, or
yes.
How does it work in that specific space?
Yes. Yes. I wanted, we had a discussion about Pete at the beginning. I wanted the presentation here to focus more on the challenges and the work that's being done. I have another presentation that was presented a while ago on data beers that had more to do about the challenges due to the volumes of data. Because here we're talking petabytes, let's say, just the Earth at 1 meter resolution is half a petabyte a day, okay? So there's a lot to be done there. The interesting thing is also here that you have different communities that have developed different platforms that are relevant for us. Of course, you have the typical data stacks of the big data community, the traditional stacks that you're talking about of the big data community. But this is very particular data because it's geolocalized data. So there's some things that are easier in the sense, for instance, if you have multiple data sources, it's pretty straightforward how you stack them one on top of the other in order to have all the information because they refer to a particular point. So there's a lot of work related to that, to managing geographic information that has been developed like for searching in geographic information like Postgres, GIS, specialized for geographic information system that has been developed in the GIS community. And then you have all the more machine learning, let's say, tools. What we found from the beginning is that we would have to develop, and I think that the different companies that are dealing with this are pretty much in the same situation from what I've spoken with them. We have had to develop our own stack for dealing with this. So basically we're working, of course, on cloud, because this is, you cannot work locally with this kind of information. And then the rest, you know, we're using, most of the development we're doing is basically pure Python. And on top of that, we're using the traditional libraries, both for handling large amounts of data and for handling geographic information data from the Python library. So we're developing it ourselves. We're happy to show you the details of the platform if you're interested outside. Yes?
You showed the soil moisture modeling. Hi. You showed the soil moisture modeling, which I found very interesting. I'm working in the ag tech.
I heard you before better than now with the microphone.
Okay. So you showed the soil moisture modeling. Do you have also models for like penetration of this water to lower areas within the soil, or?
We don't right now. There are a lot of models for this. Once again, ground truth gets you really far, and in certain places of the world there's amazing models of geological formation that go, so you can mix that in order to infer water penetration models. There's not too much work done there's a lot of work done here from the more physical standpoint, from the traditional remote sensing or geological communities. Not much merging this with new machine learning techniques, so there's a bunch of opportunities to do interesting things there. From a remote sensing perspective, it's very difficult to do this. You would need go with sensors that go completely either fully into the infrared or into the ultraviolet. And there are these sensors, but in many cases these sensors are expensive and still not validated in terms of accuracy, so we're not using that. But already by merging this with existing geological information, there's a lot still to be done.
Thank you.